Again, it's a redskin.
What is going on, guys? Welcome back. In today's video, we're going to learn how to do polynomial regression in Python. And in order to understand how polynomial regression works and why it works, we need to understand how linear regression works first. And in this video, I'm not going to go into the details of linear regression because I have a video on that already. And I also have a video on how to implement linear regression from scratch, meaning with all of the mathematics done by us. So I have done that already. Today I'm going to focus on polynomial regression, but we're going to look at a couple of examples using linear regression to see how it works and also to see why it is limited and not sufficient if the data comes from a polynomial function, polynomial distribution, or something like that. And in order to do that, we're going to use three libraries. We're going to use NumPy, Matplotlib, and scikit-learn or sklearn. And as always, if you don't have them installed, you need to open up your command line. So cmd on Windows, terminal on Linux and Mac, and then you type pip install NumPy, Matplotlib, and sklearn. Or you can also go with scikit-learn, should be the same thing. And then we can get actually started with the whole process. And the first thing that I want to do is I want to generate some basic data that comes from a linear function that can be the distribution or the randomness can be fitted with a linear function with one line, with a linear regression basically. And then we're going to look at different distributions or more complex functions. And then we're going to try to fit them with linear regression to see that it's not enough. And then we're going to talk about why and how to use polynomial regression. So the first thing we do is we import numpy as np and we import matplotlib.pyplot as plt. And also, of course, we're going to import from sklearn.linear_model. We're going to import the linear regression because that's what we're going to look at first. So let's generate some random data. Let's say we have the x values, and the x values are essentially just np.random.rand. And we want to have the shape 101. Basically, the 1 is for making the values stack vertically, because just 100 would generate 100 values in a list or in an array. And in this way, we have them vertically stacked, which is the format that we need here for Matplotlib and also for scikit-learn, I think. So this generates just random values between 0 and 1. Nothing too fancy. Those are just the x ticks. And then we want to have the respective y values, and the y values are going to be a function of the x values. So we're going to say, for example, 4 plus 5 times x, and then some randomness to get some more noise. So we're going to use a normal distribution to get that base function. And then along that base function, we're going to use a Gaussian bell curve to just generate some random data. So np random rand n for random normal distribution, and we're going to go with 101 again. So basically just same shape. And now we can just go ahead and say plt scatter x, y, and plt show, and this should already show us the basic scatter plot of the points that we generated. Now they're always going to be different unless we set a seed. What's happening now? Okay, we're having this in the plot again. I need to disable this in a second here, but for now, let me just make my camera smaller. You can see that this is a linear function, again with some noise obviously, so we can see that the points are noisy, but we have this trend, this linear trend that can easily be fitted with a linear regression, so just with a line. And of course, if I go ahead and say something like 0.2 times that, I should have less noise, and the less noise I have, the more we're going to see the actual function that we're using. So here you can see this as well. So let me just quickly turn off this view of the plot so that we have separate windows. All right, so I turned it off. Now when I start this, we have separate windows instead of seeing this integrated in PyCharm. So we have it like that, which I prefer. And now we're going to use the linear regression to fit that data. And of course, I'm going to have more noise because otherwise it's too easy. And we're going to basically say, okay, rec equals, so regressor equals linear regression. And we're going to fit the linear regression on x and y, and then we're going to also plot the linear regression. Oh, rec.fit, sorry. So this fits the regressor on the data that we have here to find a trend. And now in order to plot that, we're going to generate some x values by saying np linspace going from 0 to 1, give me 100 values. And we need to reshape that so that it fits the matplotlib structure. And the y values are just taking these x ticks and predicting using the regressor. So rec predict x values is going to be what we have here. And now we're going to just say plt plot x vals y vals color equals r for red. And this gives us then the linear regression for those points. So you can see this works pretty well because the actual points, the actual dots that we see here come from a linear function, namely from that function 4 plus 5 times x and some noise. This is just noise. This is the function 5x plus 4. And because of that, we can find a slope like that. So because of that, this is a pretty good fit. And the less noise we have, the more we're going to see. Actually, if I go ahead now and say 0 times that, we should actually have the exact same line. Now, okay, this is of course stupid because now the line is fitted to the points here, but you can see that essentially this is the function that we're looking for, and by adding noise, we just make it a little bit more random. But at the end of the day, that works. And of course, you can also increase the noise. You can say 5 times, but then we're going to have quite a lot of noise, so you don't want to overdo that. Otherwise, it's going to look kind of random over time. But you can play around with that. I think just leaving it plus 1 times noise is fine for this particular example. And you can see this is how linear regression essentially works. We have some random data points, and then we have a function based on those x values that are random. We're going to also add a function, a linear function for distributing some points with some random noise, and then we can fit a linear function for prediction. So for those of you who don't know about linear regression at all, the purpose of such a line, the purpose of such a function is that the x value could be, for example, the I don't know, the age of a student or something, and here you could have the grade of a student. Now, this is maybe not the best example, but essentially, if you find a line like that, that means the older someone gets, the more, the better grades, or let's say this is a score, the more score in a test, or the better the score in a test they have. And essentially what you do with such a line is that when you get a new x point, so you know, for example, the student is, in this case, we have 0.8, but let's say, okay, the student is 0.8 years old. This would mean that I don't have a point here, but I can just go here, and this is my prediction. Of course, this is probably not going to be exactly right. The point is going to be somewhere here, or here, or here, I don't know. But this is a good estimate of that. So we have this linear model that basically says, okay, when you have a given x value, I can predict the y value. This is the idea of that. Now, the problem is, however, that this is quite a simple function because it is, after all, linear, and we're using linear regression to fit it, which is fine. And by the way, linear regression doesn't mean 2 dimensions. In this case, it's 2 dimensions. We use x to predict y. But of course, you can also use hyperplanes. So basically, you have 5,000 features, which you cannot really imagine. But in a 3-dimensional space, you would have x and y, and you would predict z, and then you would have a plane being the linear regression. The purpose is, or the main thing about a linear regression is that it's always flat. You don't have curves. You don't have this typical polynomial curving in there. So you just have linear hyperplanes. The problem is, however, what happens if we have a polynomial function? So let's say we have a quadratic function here. We say 5 times x squared. So 4 times 2 times x plus 5 times x squared and some random noise. We can still use linear regression to fit that. In this case, it works actually quite well. So let's maybe go ahead and change the range. We're going to say, we're going to actually not do that. We're going to say 4 times the randomness minus 2. This basically generates values from -2 up until 2 because the minimum is basically that, -2. Because here the minimum is 0, 4 times 0 is 0, minus 2 is 2, so that's the smallest value we can get. And the highest value we can get is 4 minus 2, which is 2. So we have values between -2 and 2. And here we also want to do that. So we want to say -2 and 2, because then we can see the quadratic function better. There you go. So now you can see this is the quadratic function that produces our points. And we can use a linear model because that's the line with the least error, probably. Because it's the closest to all points, but it's a line, so it cannot really fit that. And you can see that actually if I'm here, I'm getting a pretty bad prediction. If I'm here, I'm getting a quite good prediction. Here, I'm getting a bad one again. Here, it's quite good. Here, I get a bad one again. So a linear model is not enough to fit that data. And this is why we want to have polynomial regression. We want to have regression, but we don't want to have linear regression. We want to have a regression that is able to fit that data. So a quadratic regression, for example, would be a quadratic function that can fit that data. And what we do in Python or in scikit-learn to do such a thing is we don't use something called polynomial regression. We don't have that. We cannot just say from scikit-learn import polynomial regression. We use something called polynomial features. So we take the features that we already have and we create polynomial features based on those features. So we say from scikit-learn.preprocessing, we import the polynomial features. And the basic idea is that we don't have additional information, right? We don't have features to add here. We have the same information that we have now, but in order to find information that is more complex, we can take the features that we have. In this case, we only have x. X is the feature, y is the label that we want to predict, but we can't take the feature x and just square it. So we can take the feature x and square it, and now we have a new feature called x squared. It's not really new information because it was already contained in x, but I can now combine x and x squared to train a more complicated model. So essentially how I do this is, or how we do this, is essentially we create poly features. So we say poly features, or you can call this whatever you want, are polynomial features, and now we can choose degrees. Now the important thing about degree is that you don't want to overdo it. Now we're going to set degree to 2 here, and I'm going to show you later on why you don't want to pick too large numbers here. Degree 2 basically means that we're squaring. If I say degree 3, it's going to add x squared and x cubed to the features. And you can go to 10, 20, 100, whatever. You can create a lot of polynomial features. The problem is, of course, let's say you have, maybe let me open that in Paint. Let's say you have a bunch of data points. So we have, this is not good. Let me just increase the size here. Let's say we have this point here, and this point here, and this point here, and this one, and this one, maybe this one, and this one, and this one. Now, a linear function would just go with this trend here. Something like that. Not exactly. If you now go ahead and you take degree 10 or something, what's going to happen is that those points are going to be fitted exactly, because we have enough degrees, we can make a very complex function to hit those points, and it will look something like that, or somewhat like that, probably. And you might say, okay, isn't that good? Because after all, you know, this is perfect, it doesn't have any errors. The problem is, though, it's very unrealistic for a point to be somewhere here. So for example, a point could be here, which is definitely better estimated by this linear line, but because this complex line is overfitting the points, we cannot really find a good model. It's very, very overfitted and not generalized well. So that's why you don't want to use too high degrees, because the more complex the function is, the better it's going to fit the training points, but the new data is going to look something like that probably, because we can see the trend here seems to be a linear one, and you can see that the red line is way better because now this function here was trained on the training points, but those additional points are not considered, or were not considered. So this is why you don't want to use too high degree. If you know the distribution, of course, use that. So if you know it's a quadratic function, you want to use degree 2. If you know it's a cubic function, you want to use a degree 3 and so on. But usually you won't know it. So now we have this polynomial features. We're going to also include bias. We're going to set this to false. And essentially this adds x squared to the feature set. And how we do that is we say x poly, and we're going to just say poly features. Come on. polyfeatures.fit transform x. And this is now x poly. And what we do now is we just train, instead of x and y, we train x poly and y, because now we have additional information here. We don't train them all just on x, we train it on x and on x squared to predict y. And essentially, what we need to do here as well is we need to, for those, since the model is used, or the model is trained on polynomial features, we need to also use those for prediction. So we're going to generate the x values as before, and now we're going to say x vals poly equals poly features transform x vals. And then here we're going to predict on x vals poly. And we're still going to plot x vals. Now this is important. The only thing that needs the polynomial features is the regression, or the regression model. We need to feed it for training polynomial features and also for prediction, but we still plot a 2D graph. And if I didn't forget anything, this should work now. There you go, and you can see that we now have this polynomial function that fits these points. The problem, of course, is when I now go ahead and say, I mean, it's not a problem with what we did, but the problem if we go ahead and say degree 6, for example, and I'm not sure if we're going to see this here because maybe it's still going to find a good line. Okay, in this case, it just finds a quadratic line. But the problem is, again, when you use two complex models, maybe if we increase the noise here, if I go with 10 times NP random, maybe we're going to see more noise and more curves. There you go. You can see that it starts curving more, which may not necessarily be bad in this case, but the more complex it gets, the more noise you have, the more the function is going to try to target the individual points, and it's going to overfit the data. We can actually try a bit more. Let's go with not 6 degrees, but 10 degrees and a bit more noise. There you go. So in this case, you can see here, we can see a slight uptrend here. So you can see it goes like that or somewhat like that. But the function is so occupied with fitting the data as well as possible that it goes completely down. If we continue that function, it's probably going to go down, 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 down. And it doesn't make a lot of sense because the values are usually, we know the function, the values would actually go up, 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 up. But this model is overfitting the data. So last but not least, we can try to do some more complex distributions here. Let's go and say 6 times x to the power of 3 plus 2 times x to the power of 4 or something, and some noise, and then we use a function with degree, or features with degree 10. Now in this case, this works quite well. Let me just maybe reduce the noise here and increase the coefficient for the squared thing. Let's change this to 12 to see more of this cubic shape. There you go. So this is actually quite fine with 10. Again, just because you're using 10 features doesn't mean that they're all going to be weighted the same. So you can use actually 100 features, and you can give the weights, you can give 0 weight to most of the features, and then you still have a cubic function. So it's not like it cannot work. The problem is that the model will be prone to overfitting. Now we can try to stress test this and see when it completely fails. Maybe with 18. Yeah, in this case, you can see clearly what's the problem. You have this function here going like that, and the chances of this function just going down abruptly is really not high. Probably it's going something like that, maybe. I don't know. But it's not going to go like that. And this is just overfitting. Let's increase the noise one more time, and then we're going to try to find a function with the power 4. So in this case, yeah, this is probably the best example. You can see what happens here just goes straight down. This is not the distribution. So this is a problem of overfitting, whereas if I say degree equals 4, we're going to get probably the perfect fit, because that is in fact a function with degree 4. And if I reduce the noise, we're going to see, let's reduce this to 5 or something. We're going to see that this fits actually quite well the actual distribution. There you go. So that's it for today's video. Hope you enjoyed and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.